Alright guys, it is now midnight and I'm still plugging along because limits are fun. Okay, maybe they're not so fun, but they are pretty cool. Alright, so what I got here for you is a list of rules for limits. We're going to be using these rules. Now, some of them you're going to get used to using so quickly that you're not going to need to write them down anymore. Okay, but I want you to notice essentially what's happening here. Some of these will prove at a later time. Some of them should just kind of make sense, should be obvious. And others, you know, you're just going to have to accept for now. All right? So the first one should be fairly obvious. If x is approaching a number a and the function is a constant, then the function is a constant. It doesn't really matter what x is approaching it. The limit will still be that same number, that constant. Okay? This one right here shows that if we are multiplying a function by a constant, and as we find the limit as x approaches a, we can just kind of pull that constant out and find the limit of the function itself and then multiply it by c. Okay? The next three actually all kind of show a distributive property almost of limits. There's no such thing as the distributive property of limits, but that's essentially what's happening. You can see the limit of f of x, limit of g of x separately. This will be really nice when we get into polynomials and then we can take the limit of each individual piece rather than having to work through the whole thing. And again, same thing with multiplication. You can see that I can just find the limit of each individual piece and multiply them. And same thing here. I can do the limit of f of x over g of x and just divide the two limits. Of course, assuming that g is not equal to 0, and we'll see that later, where we'll make sure to just kind of point that out. Okay, so now what I want to do right now is just give you a chance to kind of work through a couple of these, use the formulas correctly in a proper manner, use these properties, just so that we can make sure that we have the idea. Alright, so the first couple of times I am going to ask you to just write it out. I know it's going to be annoying and you're going to hate it, and okay, maybe I shouldn't be leading up with this, but anyway, you'll get what I mean in just a second. Alright, so we're going to find the limit as x approaches 3 of x plus 2x minus 1. I want you to use the rules. Alright, so the first thing we're going to do is we're going to use this fourth rule because I've got an f of x times a g of x. So we're going to rewrite it as the limit as x approaches 3 of x plus 2 times the limit of x as x approaches 3 of x minus 1. Alright, now I'm going to use the third one here with the f of x plus g of x because now I have a couple of those. So I'm going to go the limit as x approaches 3 of x plus the limit as x approaches 3 of 2, and all that will be multiplied by the limit as x approaches 3 of x minus the limit as x approaches 3 of 1, and then we can go ahead and find each of those limits. The limit as x approaches 3 of x should be straightforward. As x approaches 3, x is going to get closer and closer to 3. The limit of a constant, according to the first rule, is a constant, so that'll be plus 2. And then over here, again, limit of x as x approaches 3 will be 3. And the limit of a constant, again, is a constant, leaving us with 5 times 2 equals 10. Alright, so pretty easy. You probably could have done that all in one step, but again, I'm trying to show you, get you familiar with the different rules. Alright, now maybe this one will be a little bit, let's just look at one more. I want to make sure that we include this idea of the division. So I'm going to write the x limit as x approaches 1 of x squared plus 2 over x minus 2. Now to make this one a little bit more interesting, we're going to sing it. So the first thing we're going to do is we're going to notice that there's a division here, so we can do f of x divided by g of x. So we rewrite it as the limit of x approaches 1 of x squared plus 2 divided by the limit as x approaches 1 of x minus 2. But remember, that only works if the limit as x approaches a of g of x is not 0, which means that x cannot be 2. Because if x was 2, 2 minus 2 would be 0, and the limit as x approaches a would be 0. So we want to make sure to make that point over here on the side. And then I've got 2 polynomials. So I'm going to use rule number 3 over here. And I'm going to rewrite it as the limit. I don't need a line there, but I do need the x approaches 1 of x squared plus the limit as x approaches 1 of 2. Again, it's still division. That's okay, division, because we all like division. Limit of x minus the limit as x approaches 1 of 2. And then we can find all the limits just like this. The limit as x approaches 1 of x squared is 1. Plus the constant, which goes back to rule number 1. Divided by the limit of x approaches 1 is still 1. And the limit as x approaches 1 of 2 is still 2. 1 plus 2 is 3. 1 minus 2 is 1. But maybe it's negative 1. And when I divide, I got negative 3. There you go. We're done. We found the limit. Now, as I say, you're probably getting used to the idea. You probably don't need to write it out every time. But, like I say, for the first couple of times, I just want you to get used to the different rules. See how they work. Just get used to it. Alright, now actually what I'd like to do now is I want to look at x approaching infinity, because that's a little bit different. Alright, and different is okay. Different is okay. We like different. There's no problem with different. Alright, so let's look at, just really quick, the limit as x approaches infinity of 1 over x. What would happen is x got really, really big. And actually this doesn't need to be 1. This can be any, ooh, don't go away. This can be any constant here, right? It doesn't really matter what a is. As x gets really, really big, as it gets closer and closer to infinity, this number on the bottom is going to be bigger than the number on the top. And so I'm going to get closer and closer and closer to 0. Of course, I won't ever get there, but that's not what the limit is. The limit is not what happens when you get there. It's what happens when you get close. All right? Now, by a similar strand of reasoning, we can say as x approaches infinity of x over x squared, we will again get 0. Note that if x was 10, it would be 10 over 10 squared, which is 0.1. If x was 100, so that would be 100 over 100 squared, which would give me 0.01. I could keep going with 1,000 and then 10,000 and a billion, and this number would get smaller and smaller and smaller because it's approaching 0. Of course, the other way you can do it is cancel out the x's, and you would end up with 1 over x. Because x is not 0, x is approaching infinity, so it's okay to cancel out the x's. And again, you would be back to this rule right here, which says that as x approaches infinity, a number over x will always give you 0. So a couple of different ways to support that idea. So let's look at that in action. Yes, look at it in action. We got the limit as x approaches infinity of 2x plus 3 over x minus 4. Now we've seen this before, something similar to this. We didn't talk about it in terms of the limit. We just said, we came up with a couple of rules. We said we can put big numbers in for x and see what this is getting close to. We said that we can actually just look at the highest degree variable there and divide and get the answer that way. Those are all just kind of rules of thumb, shortcuts, easy ways of doing it. We now know how to deal with limits. We know that essentially the limit's going to distribute to each of these pieces. Now I don't really want to do the limit as x approaches infinity of 2x because that'll be 2 infinities, and I don't really want to have to deal with infinities. So what we're going to do is multiply by a creative form of 1. Now this is the most creative form of 1 that you probably have seen in a long time. Though when you deal with complex numbers, you do some pretty creative forms of 1s there because you got complex numbers and all that fun stuff. But I'm going to multiply by 1 over x times 1 over x. Now why 1 over x? Because that's the highest degree variable right here. Alright, now watch what happens when I do that. I'm still going to have the limit. I haven't done the limit part yet. It still needs to be there until I actually do the limit. So I'm going to have 2x over x plus 3 over x divided by x over x minus 4 over x. Now you may say, but now that's ugly. Okay, yeah, it's ugly, but look, the x's cancel out here, the x's cancel out there, leaving me with 1, and so I now have the limit as x approaches infinity of 2 plus 3 over x over 1 minus 4 over x. And you say, but that's still ugly. Okay, yes it is, but note that with what we talked about over here, this now makes the limits really nice and the infinities all go away. Because I can take the limit as x approaches infinity of 2, because that's still just 2. I can take the limit as x approaches infinity of this fraction, because that's this situation over here, where as x gets really big, that's going to become 0. I can take the limit as of 1, because that's a constant, and again, this one's going to be 0 because of what we talked about before, giving me an answer of 2, which is the same answer that we came up with at the beginning of the year, several months ago when we were looking at asymptotes and rationals and all that kind of stuff. But the difference is now I can do this a little bit, I can do it formally. I can actually mathematically prove what I'm getting. All right, let's look at one more. Let's look at the limit as x approaches infinity. And let's, what the heck, let's throw in a squared now. Oh yeah, I did. So same idea, right? Multiply by a creative form of 1 that's going to simplify it. I really don't want to have to put the infinities in here. Infinity squared minus 3 infinity, I have no idea what that's going to give me. It's going to give me something close to infinity squared, I assume. But infinities are just weird to work with. So we're going to multiply by 1 over x squared over 1 over x squared. Now notice this time we did x squared. Why is that? Well, that's the highest degree variable. And so that's the one that I want to divide by. So I'm going to end up with x squared over x squared minus 3x over x squared plus 2 over x squared all over 1 over x squared minus x squared over x squared. I got a lot of x squareds in there, and yes, it's ugly. It's still the limit as x approaches infinity. But note again, these are going to cancel out, giving me 1. These are going to cancel out, giving me 1. And I can do the limit of everything else. The limit as x approaches infinity of 1 is 1. This one right here, if the x cancels out, it'll leave me with an x on the bottom. It's 3 over x, which is this right here, which means that it's 0. 2 over x squared is also going to be 0. So I got another 0. On the bottom, I'm going to have 0 minus 1. And so I have 1 divided by negative 1, which is negative 1. So I got the answer. All right? So I want you to recognize that that's kind of what's going on. Okay? Now, just to kind of top this off, what's the point of this? Well, now we can find all the asymptotes we can discuss in behavior using the idea of limits. So, you know, we've already got this one. Let's go ahead and work with this one. Let's find the asymptotes. Now, remember, we're going to find the asymptotes by finding, let's do vertical asymptotes first. Vertical asymptotes are when the bottom equals 0. So 1 minus x squared equals 0. But remember, we got to check the top. So let's check the top too. We're going to factor the top. It's going to be x minus 2 and x minus 1. The bottom is going to factor to 1 minus x, 1 plus x. Now these two are essentially the same, except they're negative of each other. So if I divide x minus 1 by 1 minus x, the result is negative 1. And so what I end up with is x minus 2 over negative 1 plus x. So I can see now that there's a vertical asymptote at 1. Okay, so what I want to do is I want to look at and figure out what happens as, sorry, not at 1, at negative 1. What happens as x gets closer and closer to negative 1? Well, honestly, the easiest way to deal with that is probably by using a sign diagram. All right, so let's sign diagram away. I've got my x-intercepts at 2. I have a hole at 1, which may be important later, but let's just mark that it's a hole. Okay, that's not an x-intercept. The sign doesn't alternate there. And then I've got a vertical asymptote at negative 1. Okay, so if I put in a number, say 0, 0 minus 2 will be negative 2, and then negative 1 plus 0 will be negative 1, I get a positive number. So I get a positive number here. It should alternate on either side, which means it should look something like this. All right, no problem there. None of these are double roots, so it should just be alternating just like that. So at -1, I see that it's negative here. So if it's negative here, it's got to be going down. It's positive here, which means that the asymptote, it has to be going up, just like that. Which means if I'm discussing the end behavior, if I'm talking about what's happening at that vertical asymptote of -1, I can say as x approaches -1 from the left, right, then y approaches -infinity. As x approaches -1 from the right, so as I come up to -1 from the right, I can say that y approaches positive infinity. All right. Now the other thing that I need to talk about is I need to talk about this other thing of my limit as x approaches infinity. Well, as x approaches infinity, it approaches -1. Now what that means is that I've got here a horizontal asymptote at -1. And so you can see here then what has to be happening for the most part. You can put in some other numbers and try to figure out if there's anything else interesting going on. But for now, we can just deal with what we have. All right, soon we're going to learn about derivatives. We're going to be able to find out a little bit better if there are little humps and other things here. But for now, we're just going to stick with this and say, well, as x approaches -infinity, what would happen? Well, as x approaches -infinity, it would approach -1. And as x approaches positive infinity, y would also approach -1. All right? And so you've got your basic idea here. You now can discuss end behavior. You can discuss the asymptotes. You can I guess we've got a hole here at x equals +1. But that's not what we're looking at right now. All right, so that kind of gives you the idea. That's it for this video. I've got one more, which we're going to look at we're going to look at natural log, we're going to look at trig. So yeah, this is where it gets insane.